Benoit Mandelbrot was born in 1924 to a Lithuanian Jewish family in Warsaw, Poland. There his father made a living by buying and selling clothes, while his mother was a doctor. In 1936, the family fled the Nazis, first moving to Paris and then to southern France to avoid getting caught and potentially executed. It was at an early age when Mandelbrot was introduced to mathematics, most of which was due to his family. In France, his uncle, Zolem Mandelbrot, who was a professor of mathematics, took responsibility of Benoit's education. It was primarily his uncle's influence that helped Mandelbrot define his style of math and thinking. Once World War II was over, Mandelbrot continued his studies in mathematics at the École Polytechnique in Paris. He then studied aeronautics in the United States at the California Institute of Technology, and later returned once again to France and completed a PhD in mathematics at the University of Paris in 1952. Mandelbrot spent most of his professional research career at International Business Machines, or mostly known as IBM, Thomas J. Watson Research Center in Yorktown Heights, New York, beginning in 1958. It was IBM who first made the personal computer popular. It was here at IBM where Mandelbrot was given an environment where he was allowed to explore a wide variety of different ideas. In other words, he was basically free to follow any research he wanted to pursue in applied mathematics. While working for IBM in the 1960s, Mandelbrot had begun to focus his attention on fractal mathematics, beginning with his article, How Long is the Coast of Britain? Statistical Self-Similarity and Fractional Dimension, published in Science, 1967. In this article, he introduced fractals as a way to solve the problem how to measure a curve as complex as a geographic coastline. Here he introduced two characteristics of fractals. Self-similarity, a never-ending pattern that repeats itself at different scales. In looking at this image, self-similarity is evident. The fractal looks the same over all ranges of scale. Going from a large triangle to a small triangle, you can tell that the image has the same main components no matter the size. Here you can see step by step how to create two famous fractals, the Sierpinski gasket and von Koch snowflake. Fractional dimensionality is the ratio comparing the complexity and detail of a fractal pattern. This can be changed based on the scale at which it is measured. Fractional dimensionality was a new concept for scientists. For a long time, they saw objects as either having one dimension, two dimension, or three dimensions. A one-dimensional object is a straight line. A two-dimensional object is a surface with no thickness, for example, a flat piece of paper. A three-dimensional object has height, width, and thickness. In Mandelbrot's concept compared to others, he believed objects could have a variation of dimensions. For example, an object can have a 2.5 dimension. It's basically an object between a second and third dimension. By using this newfound concept, he showed that things typically considered to be rough or chaotic, like clouds or shorelines, actually had a degree of order. From this research previously mentioned, he created the Mandelbrot set, which is found by the formula Z n plus 1 equals zn to the second plus c. Basically, the formula works by obtaining an input and running it through the function to calculate the output. Once the output is found, it is then used as an input in the same function. Continue doing this process an infinite number of times to then create a fractal pattern. Here's an example of zooming into a fractal that was found by using the previous equation. The use of fractals is used every day in multiple industries like the manufacturing of cell phones, movies, medicine, biology, etc. In the movie industry, fractals are used to create realistic visual effects as found in the Star Wars movie The Revenge of Sith.
The same kinds of fractal design principles have completely transformed the magic of special effects.
This is a key moment from Star Wars Episode 3, where our two heroes have run out onto the end of this giant mechanical arm, and the lava splashes down onto the arm. My starting point here is to actually take the three-dimensional model and take essentially a jet and just shoot lava up into the air. This looks kind of boring. It's doing roughly the right thing, but the motion has no kind of visual interest to it. Let's look at what happens here when I add the fractal swirl to it. Where this becomes fractal is we take that same swirl pattern, we shrink it down and reapply it. We take that, we shrink it down again, we reapply it. We shrink it down again, we reapply it. And from here on, it's just a case of layering up more and more and more. I've used the same technique to create these additional lava streams. I then do it again here to get some just red hot embers. Then we take all of those layers and we add them up and we get the final composite image. My hero lava in the foreground, the extra lava in the background, the embers, sparks, steam, smoke.
In medicine, the rhythm of a heartbeat can be accurately portrayed by using fractals. Fractal analysis of CT scans can also quantify the health of lungs suffering from pulmonary illnesses. In medicine, fractals are used to analyze cancerous tumors. Researchers at Harvard Medical School and elsewhere are using fractal analysis to assess the health of blood vessels in tumors. By using fractals, one can measure irregular structures and therefore help provide the explanations to differentiating cancers. Even fractals are found in our cell phones. In the industry of cell phones, the use of fractals led to the development of more efficient antennas. Previously, cell phone antennas were limited to only a few frequencies, but now with the use of fractals, antennas are smaller and able to receive a lot more frequencies. In 1999, Dwight Jaggard and Douglas Werner found cell phone antennas arranged in a fractal pattern were superior in transmitting radio signals over other arrangements of the antenna. For all his hard work, Mandelbrot received numerous honors and prizes in recognition of his remarkable achievements. For example, in 1985, Mandelbrot was awarded the Barnard Medal for meritorious service to science. In 1986, he received the Franklin Medal. In 1987, he was honored with the Alexander von Humboldt Prize. In 1988, he received the Steinmetz Medal. In 1991, he received the Nevada Medal. In 1993, he received the Wolf Prize for Physics, and many more awards. Therefore, by having the discovery Mandelbrot provided, We would not have many of the fractal-induced technology that are found today.